Hello everyone, welcome to C2 integration part 2. In part 1 we looked at integrating some functions, indefinite functions, so when we integrate we get a plus c, a constant of integration. This time we've got some limits, and just below the integral and at the top of the integral we have some numbers, 1 and 2. And we'll look at what this means in terms of graphs in a minute. Let's see how we'll do this using algebra. So the first thing we'll do is just integrate our function over here, so 2x minus x squared. So we know we raise the power by 1, so you get a 2 there, divided by that raised power, plus, minus, in this case, minus x cubed divided by 3, so again, and we use square brackets, and we write our limits here, 2 and 1. And then we substitute the 2 in, so you've got x squared, so you'll write 2 squared, take away 2 cubed divided by 3, and put brackets around it, and it's always a minus. And then you substitute the 1 in, so you got 1 squared, take away 1 over 3. And so this will give us 4 minus 8 over 3, minus 1 plus 1 over 3. If we add that together, that should give you 2 over 3. And so what you'll find is our general rule is, if we're going to integrate anything, we've got limits a and b. B is always the bigger number of some function fx dx. And say when we integrate fx, we get a new function gx, or in fact let's use, in this case we got f prime x, and when we integrate that we get fx, so we can write fx, okay, so this would equal fx, and you put b and a, and then we'll write an f of b take away f of a. So let me go over that again. If you've got some function f prime x, when you integrate it you get fx, then the limits b and a are integrated. This is a definite integral, and it's always, you substitute the b in there, subtract it from when you substitute the a into the fx, and then you get an answer. Now we don't write the constant of integration. This is a definite integral because it has a definite value. Now you may be wondering what this means, so let's look at the graph of the functions. We've got minus x squared plus 2x, and if we put x equals to 0 we get y equals to 0. If we put y equals to 0 we'll get x and minus x plus 2, so therefore x equals 0 or x equals to 2. We know x is a is less than 0, therefore it's a sad shape, and therefore 0 and 2, and it'll probably look something like that. And there's y and x. And what we've done, we've integrated from 1 to 2, minus x squared plus 2x dx. Now there's our 2 and there's 0. Now this integral has in fact given us the area between 1 and 2. So this area here is given by this integral. So we write area under the curve between x equals 1 and x equals 2. So it'll always form the area bounded by the curve and the x-axis between our limits 2 and 1. So to recap, to go over that again, when you integrate, when we use definite integration and we use some limits, then the definite integral gives us the area bounded by the curve and the x-axis specified by those limits. Right, let's integrate this function 3x squared take away 4x, between 2 and 0, and we're going to show it gives us 2. So if we integrate it, we get 3x squared raised to the power by 1, so you get 3x cubed divided by 3 minus 4x squared divided by 2, and we'll put our limits there as 2, 0, and that gives us x cubed take away 2x squared, and we'll put down 2, 0. If we substitute the 2 in, we get 2 cubed, which is 8, take away 2 squared, which is 4, times 2, which is 8, and we'll get 0. Now why does that happen? To see why that happens, we'll need to draw a sketch of the curve. So we've got fx equals 3x squared take away 4x. Let's factorize this, so we'll take out the x's, and we've got 3x take away 4. And if we set this to 0, so make x equals 0, we get y equals 0. Make y equals 0, x equals 0, or x equals 4 over 3. We also know a is greater than 0, therefore it's a happy shape, and we can do a little sketch, and it should look something like this. So you want to come down, it's a happy shape, go up. Now this point here is 4 over 3, and the other root is at 0. Now 2 is somewhere, say around about over here. Now what we'll find is there's a region below the x-axis, and this region here will give a negative integral, and the region above the x-axis will in fact give us a positive integral. And so what we've got to do is do the integral separately if you want to work out the total area. So we'll integrate, and this is something you might want to have a go at and check. If we integrate from 4 over 3 to 0, and we'll integrate fx, we know what we've defined fx already, this should give you minus 32 over 27. And then if we integrate from 2 to our next root, so the green region, 4 over 3, fx dx, this should give you positive 32 over 27. Now bear in mind this is a negative, so when you add them together you get 0. So our total area we can simply write as being 32 over 27 plus 32 over 27, which gives us 64 over 27. So if you're watching this video and you're learning some calculus, it's worth having a go at these integrals. So fx is 3x squared, take away 4x, integrate them from 4 over 3 to 0, and 2 to 4 over 3, and you should get a total area of 64 over 27. Now sometimes you might have really complicated functions that we can't integrate yet, probably when we do second year A2 maths, or even at university. In order to compensate for that, we can use a trapezium rule. So if we have a curve, say, that looks something like this, and let's say we've got, I don't know, here we go, something like that, and we've got some points here, let's call that A and B. And we want to work out the area between them, and it's a really complicated function. What we could do is divide this strip A and B. We can divide this region up into strips. So let's divide them up. Here we go. And so they're equal width, and so the width, let's use h for width, will be the length B take away A divided by the number of strips I've got. So 1, 2, 3, 4, I've got 4 strips, so I'm going to divide it by n, which is the number of strips. So in this case it's B take away A divided by 4, where n equals 4. So let me just put n equals number of strips, and the width is h, the width of each strip. Now if we were to apply the trapezium rule to one of the strips, let's call this length y0 and this height y1. Then we know, and let's call this area here area 1. Then we know area 1 equals y0 plus y1 divided by 2 times by the width h. And if we were to continue doing that to all of the strips and add them up together, we'll get a formula where our total area is equal to, again it's approximation because it's a trapezium rule, is h over 2, and it will be our first strip plus the last strip, yn, which will be this strip here. Okay, and all the other strips, all the other lines, sorry, they get counted twice as we go through. So we've got y1 plus y2 all the way to yn minus 1. Okay, and there's our formula for the trapezium rule, and we know that h is b minus a divided by n, and n is the number of strips. So let's apply the trapezium rule to a problem and see how it works. Okay, say we had to work this out using the trapezium rule, and let's just say n equals 6 strips. Okay, so we're going to work out this area using the trapezium rule with 6 strips. Okay, so what the first things we could do is in fact to draw a little box. That would probably be helpful. A little table, we can have x over here and y over here. Let's just draw a straight line. And we'll start from 0, and we need to go up. Now we know that h equals b take away a over n. So b is 3, a is a lower number, so it's 0, divided by number of 6, which is 6, number of strips, which is 6, and so this equals 0.5. So we go up 0, and 0.5, 1, 1.5, 2, 2.5, all the way to 3. And the y values we can work out by substituting these corresponding x values into 1 plus x square root. So you get 1 square root of 1.5, square root of 2, square root of 2.5, square root of 3, square root of 3.5, and that should give us 2. We can then apply the formula for the trapezium rule, where our area approximately equals h over 2. So we've got a quarter. Let me just write down the formula. So we've got h over 2 y naught plus y n plus 2 times y1 plus y2 all the way to yn minus 1. And so we've got h, which is a half, divided by 2 gives us a quarter. And then we've got 1 first term plus the last term, which is 2, plus 2 times everything in between. So we've got 2 times 1 plus square root of 5 plus square root of 2 plus 2.5 plus square root of 3 plus square root of 3.5. Okay, and that then gives us 4.661488. It goes on and on and on. And so there's approximation to the area. Now the trapezium rule is quite accurate. To test it, for the example we've just done where we've got 6 strips, we had the area approximately equals to 4.661488. Now the actual value is 14 over 3. So to work out the relative error, we can do, so the relative error equals the approximation, take away the actual value, divided by the actual value. So this will be equal to 4.661488 take away 14/3. Okay, we're using modulus because we're just interested in the difference. Divided by 14/3, and this gives us 0.00111. If we were to multiply that by 100, it will give us the percentage error, relative percentage error, which is 0.111. So within 1% or 0.1% of an accuracy is not too bad with 6 strips using a trapezium rule.